Hello! Thank you to the organizers of this RMP live paper series, and thank you to you for tuning in. My name is Scott Rodilitz. I'm a fifth-year PhD student at the Yale School of Management, and I'm going to be presenting on some joint work with Vahide Manshadi called Online Policies for Efficient Volunteer Crowdsourcing. Now, we think our work can be applied broadly to crowdsourcing platforms, but for the purposes of this talk, I'm going to focus mainly on food recovery before touching briefly on these broader applications at the end of the presentation. For now, let's dive into food recovery. So why is food recovery important? Well, in the US, we waste a ton of food. In fact, we waste over 60 million tons of food each year, and simultaneously, there's 37 million Americans who live in food insecure households. Now, to correct this mismatch, it seems like all we need to do is take food from where it's being wasted and bring it to where it's needed. But unfortunately, this elegant solution poses two key operational challenges. First, it's hard to make connections between potential food donors and potential food recipients. And second, even once these connections have been made, transporting the food between these two parties can be costly, especially the last mile transportation. Now, luckily, we live in a day and age in which online platforms have stepped up to address all sorts of societal problems, and this is no exception. Many platforms have emerged to address these issues, and I'm not going to go into details about many of them. Suffice it to say that they frequently use volunteer labor to facilitate the costly last mile transportation. Now, I will give you a bit more detail on Food Rescue US, which is a group that we've been collaborating with for the past few years. Now, at a high level, Food Rescue US has had a pretty significant top-line impact, delivering over 30 million meals in cities across the US. They're active in over 33 locations, and in each of those locations, there's a site director. Now, site directors are in charge of making connections between potential donors and recipients. And once they've made these connections, they post a schedule to the Food Rescue US app and website where volunteers can sign up. Now, if the time of these rescues gets close and a volunteer is not signed up, site directors frequently turn to nudging mechanisms to encourage volunteers to sign up. And that's what our research is focused on. How can we efficiently nudge volunteers to minimize the number of missed donations? Now, when we think about notifying volunteers, there's a few considerations we have to keep in mind. First, these notifications need to be infrequent. I'm sure you've all downloaded an app that immediately inundated you with notifications. You probably quickly silenced those notifications or even deleted the app entirely. And that's obviously something we want to avoid in this context. In addition, because we're dealing with volunteers, we can't require a quick response. We can't even require a response at all. Now, these considerations come from our conversations with site directors, but they're also consistent with literature on volunteer management. Taken together, they paint a pretty challenging picture within which we need to operate. And to motivate that, let's look at a toy example. So, suppose we can notify each volunteer every 2 days. Suppose we have 2 volunteers and there's a donation available today. Now, we can notify neither volunteer, we can notify 1 volunteer, we can notify 2 volunteers. Because we can't require quick responses, sequential notification doesn't make, it's not practical. We have to make a one-time decision. And to maximize the probability that someone picks up this donation, we can notify both volunteers. But then tomorrow, when a donation arrives, neither volunteer is available to pick up this donation. And so it goes unfulfilled. Now, this is a pretty classic OR trade-off between maximizing the payoff that we get today by notifying more volunteers versus maximizing the payoff that we can get tomorrow, which could be achieved by saving more volunteers for the future. Now, I want to remark that current FRUS practice is to notify volunteers at most once every 7 days. And when site directors make notification decisions, they do so in a manual and ad hoc way. So one of the ways we think we can help is by first identifying which volunteers are best to notify about which tasks. So to do so, we took the characteristics of each rescue, so things like time of day of week, pickup location, drop-off location, And we were able to reduce these via principal component analysis to look at whether volunteers have predictable and stable preferences. So each color here represents a volunteer. The size of each circle represents the number of rescues with a set of characteristics that that volunteer has completed. And I want to highlight for you that there is a lot of clustering going on by color. This suggests that volunteers do indeed have consistent, stable preferences. And to back this up, I've shown on the right that we can make pretty accurate predictions using simple, interpretable machine learning techniques, such as k-nearest neighbors. So using this historical data, we want to answer the question of how we can improve the notification decisions that Food Rescue US makes. And that brings us to the meat of our presentation. The first thing we're going to do is introduce the online volunteer notification problem. It's a pretty general framework, but it's also a really intractable problem to solve optimally. So instead, we're going to develop online policies with constant factor guarantees. Now, to evaluate these online policies, we're going to compare them to hardness results, and we're going to test them on data from Food Rescue US. So with that roadmap in mind, let's take a look at the model. So the online volunteer notification problem is a generalization of online stochastic bipartite matching. We've got a set of volunteers V and a set of donation types D, and donations are going to arrive according to a known time-varying probability distribution. This is pretty standard in the literature, but volunteers are always in the system. They're just in one of two states, active or inactive. Initially, all the volunteers will start as active, and if an active volunteer is notified about a donation, she's going to respond according to her match probability, which is pair-specific, and which we discussed just a moment ago, can be estimated reasonably accurately from historical data. If an active volunteer is notified, she's going to become inactive for tau periods, and this inactivity time is our way of modeling the adverse impact that notifications have on volunteer engagement. You can think of it as a time during which volunteers silence their cell phones. Now, this interactivity time is governed by some distribution G, which we're going to leave general. And as you'll see later, our results are parameterized by a feature of this interactivity time distribution. Now let's take a look at how our toy example incorporates this notation. So suppose we can notify each volunteer every 2 days. This corresponds to a deterministic interactivity time of 2. We've got 2 volunteers, each with her own pair-specific match probability. And if we notify both volunteers, as long as one of them responds positively, this donation does get completed. However, both volunteers are now inactive, and so tomorrow if a donation arrives, neither volunteer will respond to a notification, and so this donation does not get completed. Obviously, that's unfortunate because our goal is to maximize the expected number of claimed donations over our time horizon. Now, I want to emphasize that this is a submodular objective function. It's challenging because it depends jointly on the actions of all volunteers. So this represents an underlying high-dimensional dynamic system. And in addition, the states may be partially observable if this interactivity time distribution is at all stochastic. Thus, we're not going to be able to solve this problem optimally. It's intractable. Instead, we design online notification policies that are simple, that are computable in polynomial time, and that perform well compared to a benchmark. Now, before getting into that benchmark, I want to highlight that we contribute to 2 main streams of literature with our work. On the application side, what we do is related to volunteer operations and staffing. And on the technical side, our work is related to online reusable resource allocation, as well as profit inequalities. There's a lot of great work here. I've highlighted just a few. If you have questions, I'm happy to talk about these works and how we relate to them offline. Getting back to our benchmark, when we think about a benchmark, we should think about a clairvoyant solution that knows in advance the arrival order of donations, as well as the state of volunteers in each time period. And in the paper, we're able to show that we can upper bound this clairvoyant solution with a linear program benchmark. And we do this by first upper bounding our submodular objective function with a piecewise linear one. And we then introduce a key constraint on the frequency of notifications that volunteers receive relative to the interactivity time distribution. Now, when we solve this linear program, we get a solution x star, where x star VDT represents the probability of notifying a volunteer V conditional on donation D arriving at time T. Now, one immediate possibility would be to probabilistically follow this linear program solution, but unfortunately, this does not give us a constant factor competitive ratio. And this is because even though it meets this key constraint in expectation, for a particular arrival sequence, this constraint may be violated, which means that volunteers may be inactive at inopportune times. Now, in the paper, we're able to get around this by introducing some adjustments. And before getting into those details, I'm going to highlight at a high level the results that we're able to prove. So our theoretical results are all parameterized, as I mentioned, by a feature of this interactivity time distribution. In particular, they're parameterized by the minimum discrete hazard rate, which we denote by Q. Now, the minimum discrete hazard rate is equivalently the minimum probability with which an inactive volunteer transitions back to being active. So if Q is larger, that means volunteers, after being notified, are more quickly returning to the active state. As you might expect, that means that our lower bound, given by this green curve, and our upper bound on the performance of any online policy are both going to be increasing in Q. Now, this upper bound comes from two hard instances, one of which is particularly challenging when Q is small but positive. I'm not going to get into the details of these instances here. You'll have to read the paper for those details. But I will talk to you a bit about the lower bound that we establish. Now, this lower bound comes from two policies, both of which have equal competitive ratios. And I'm going to talk to you in depth about one of those two policies. The policy that I'm going to talk about is our sparse notification policy. And we start with a feasible ex-ante solution, X star. Now, in the paper, we discuss ways to design good ex-ante solutions, but for now, just think of it as the solution to that LP benchmark that I discussed earlier. And recall, we need to adjust the solution in some way. And we do this by solving a sequence of low-dimensional dynamic programs. Now, one of the key challenges of the online volunteer notification problem is that the objective depends jointly on the action of all volunteers, right? That's a high-dimensional dynamic system. But we get around this by introducing an artificial priority among volunteers, which allows us to decouple the contribution of each volunteer. And instead of solving this high-dimensional dynamic program, we instead solve a low-dimensional dynamic program for each volunteer. Now, to be specific, starting with the top-ranked volunteer and starting at the end of the time horizon, for every possible donation that arrives, we're going to construct a sparsification, meaning that we're either going to probabilistically follow our ex-ante solution, or we're not going to notify the volunteer. And we're going to make that determination by comparing two different rewards. The first is the is the reward that we would get from notifying this volunteer about a particular donation at this time. And the second is the reward that we would get from saving this volunteer for the future. Now, the reward that we get from notification has two parts. First is the immediate reward, meaning the probability that this volunteer is the one that completes this donation. Now, according to our artificial volunteer ranking, this happens if she responds and if no higher ranked volunteer does so. Now, for the top ranked volunteer, this is easy to compute. It's just whether or not she responds. For lower ranked volunteers, it depends on the sparsification solution for higher ranked volunteers, which is why we need to solve these dynamic programs in sequence. Now, after being notified and potentially responding, this volunteer becomes inactive and will become active again as governed by this interactivity time distribution. When she becomes active again, she gets a value to go in that time. Alternatively, if we don't notify this volunteer, she gets her value to go from the subsequent period. Starting at the end of the time horizon and working backwards, we're able to compare these rewards, compute these values to go, and ultimately compute the sparsification. We do this for the top ranked volunteer first, then the next ranked volunteer, all the way to the lowest ranked volunteer. And in the online phase, we simply follow this sparsification probabilistically. Now, in the analysis, we formulate a linear program that lower bounds the competitive ratio of this policy, and we find a feasible solution to its dual. This primal dual analysis reveals that the competitive ratio of our sparse notification policy is 1 minus 1 over E times 1 over 2 minus Q. This has two parts. The first comes from our submodular objective function, and the second comes from this sparsification procedure I just described. Now, as noted, we have another policy called our scaled down notification policy, which, as the name suggests, takes an ex-ante solution and scales it down. That policy achieves the same competitive ratio, but in practice, it doesn't exhibit as strong performance as our sparse notification policy. And to highlight that, let's look at some numerical performance. So here, I've shown you test results of the sparse notification policy on Food Rescue US data from various locations. We followed Food Rescue US's convention of notifying volunteers at most once per week. So this means our interactivity time distribution is deterministic, equal to 7 days. And we've compared ourselves to heuristics representing the current practice of Food Rescue US, namely notifying a small subset of volunteers. And as you can see, across locations, the sparse notification policy exhibits superior performance. We're extremely encouraged by these results, and we're looking forward to implementing our policy in the near future. Now, I want to take a moment at the end of this talk to emphasize that our approach, though I focused on food recovery and Food Rescue US, can be used more broadly to improve the efficiency and engagement of notification systems. Now, this is a big problem, both for volunteerism, where 30% of volunteers churn each year, and beyond, where notifications are extremely important, but also contribute to marketing fatigue, which has significant negative consequences. Now, we think our framework provides an avenue to study these trade-offs in a rigorous way, and we think it can be very helpful in answering a lot of the questions that arise in these domains. Thank you very much for your attention, and I'm happy to answer any questions you may have.